For 10.1, we're going to be starting to look at two-sample, two-proportion tests. So when you are trying to compare two different populations or groups, we opened class with just looking at a comic strip, looking at the relationship between, in this case it's a little bit ridiculous, but jelly beans and acne. So they are going to test each of the types of jelly beans, different colors and flavors, at the 5% level. And this is on OneNote, but notice that they have all the different colors and varieties, and I think they may have started making one up, some of them up as we go. Notice here's the panel that is different. There is a link between green jelly beans and acne, which is surprising, and keep going, and the rest of them are not. Headlines, green jelly beans, linked to acne, which was what you would get at both 5% significance level and a 95% confidence if I was doing an interval. The point of the comic strip is that when you have 20 tests, in this case, that is why there are so many different colors and flavors of jelly beans given, then a 5% significance means that if there's a 5% chance that you make the wrong conclusion, that type 1 error, that is the equivalent of saying that 1 out of 20 of the test will have a significant result, even if there is no real-life basis for suggesting green jelly beans cause or influence acne. Okay, so you can make all the arguments about food dyes that you want, but just keep in mind that when you run lots and lots of tests, some of them will come up with significant results when they really shouldn't, just based on actual influences. Okay, for 10.1, we're going to focus specifically on comparing two proportions, so two-proportion z-test, because proportions are always z's. We'll be looking at the difference between the two proportions for our two populations. We'll be comparing the null hypothesis of P1 is equal to P2 versus an alternative of P1 is either less than, greater than, or not equal to P2. Our conditions: both samples should be randomly selected or treatment should randomly be assigned. Both samples, that means each sample, should be less than 10% of their respective populations if it is a sample, or the results of an experiment should be independent of one another. And then for normality, you have two options. You can either use N1P1 and N1 times 1 minus P1. That should actually be, that is not a typo, the P1 from our sample. Notice that when you have P1 versus equals P2, those are both going to be letters. You're not going to have P1 equals 0.5 or something like that. So once again, just like with intervals, we're going to have to fall back to our sample data. So unlike the one proportion test where we use the P from our hypotheses, for two proportion, we'll have to use the P from our data, just like with our intervals. Anyway, do basically the four N's times P's that we had to do for intervals, or a new option that you have for hypothesis test is the N1 and N2 times P hat C and 1 minus P hat C. So what is that? P hat C is the combined proportion. So it is the count of successes out of both samples over the count of all the individuals. So in other words, you add the numerators and the denominators. So how many out of both samples had whatever characteristic out of the total number in both samples. And that will be used also in our z-test statistic. So the condition is not the only time you would be using it. So I'll leave it up to you if you want to use N1 and N2 like we did for intervals with the conditions. You can, but be aware of the fact you will have to eventually calculate P hat C for our z-test statistic if you're doing the formula method. Okay, so our z-test statistic would be the difference in the proportion, the sample proportions, P1 minus P2, minus that 0, because keep in mind our null hypothesis is that there is no difference between the two. So this is really, in essence, the difference in the sample proportions minus what we suspect would be the difference in the population proportions, or nothing. And then over the combined standard error of our two samples. Notice we're using P hat C's here over each individual sample size. First example, working one all the way through, we have two schools. Some students, unfortunately, at each of them, who did not get to eat breakfast that morning before they came to school. The schools are interested in whether there is a significant difference in the proportion of students at each school that do not get breakfast before they come to school. So they get a random sample of 80 students from the first school, where 19 had not eaten breakfast, and 150 out of the second school, where 26 had not eaten breakfast. So I wish to test at 5% significance the hypotheses of null is equal, that P1 is equal to P2 versus the alternative that P1 is not equal to P2, and then define what P1 and P2 are, where P1 is a proportion of students who don't eat breakfast at school 1, and P2 is the equivalent proportion at school 2. This is a two-proportion Z test. Do make sure you write that out and not use the calculator abbreviation. Both samples were simple random samples, so therefore they were randomly selected, and they can be considered independent. We were given that there are 1,500 students at each school, so both of the sample sizes are below or at equal to 1/10 or 10% of that sample population size. So we have independent conditions met. I went ahead and calculated what P hat C was. So there was 19 out of 80 students at the first school and 26 out of 150 at the second school. So 19 and 26 gives me 45, 80 and 150 gives me 230, gives me a combined proportion of 0.196. You could go ahead and calculate P1 and P2 here, P hat 1 and P hat 2 if you wanted to. We'll need that eventually, but not yet. Take each n times this combined P hat and 1 minus the P hat. And notice that the normal condition is met because all of these end up being a product of at least 10. Then for our reduce step, if you haven't already somewhere, calculate P hat 1 and P hat 2, then use that in our Z calculation. So Z is equal to the difference between school 1 minus school 2. Make sure you subtract them in the same order that they came in the hypotheses, minus the suspected difference for our populations, which would be 0, over the combined standard error using P, C in the numerators of each, and I get a Z value of 1.17. Okay, so you have I clipped an illustration from the book. Here's the 1.17, just a little over 1 deviation on either side of the mean. So I look at my chart, and from my Z or table A or Z table, I look up positive 1.17 just because that's what I'm given, and I get 0.8790. Now 0.8790 is actually the area to the left. So if I want to know this area in the tail, I need to take 1 minus, which is 0.121. And then because it's a not equal to hypothesis, alternative hypothesis, I need to multiply that value by 2. So once again, I can do this 1 minus and then multiply by 2, or I can take the symmetric tail over here, negative 1.17, which would just go ahead and give me the 0.121, and then multiply that by 2. Either way, you have to multiply by 2, though, to get a combined p-value of a little over 24%. So at 5% significance, I fail to reject the null and cannot conclude that there is a significant difference in the proportions of students who do not eat breakfast at these two schools. So what would the type 1 and type 2 errors look like? Consequences of each. Which one would be worse? Which error could we have made? So let's go back up to the hypotheses. Type 1 is if I rejected the null incorrectly. So that'd be if I concluded that there is not a difference when there actually, if I concluded that there was a difference when there actually was not. So perhaps I think that school 2 has a higher proportion of students that don't eat breakfast. I spend money on funding additional breakfast interventions at the particular school when that's not needed. Or perhaps funds are funneled out of school 1 if it looks like they have a better rate of students who eat breakfast at home, taking money away from that school when they actually need it. Type 2 would be failing to reject the null. So if I do not say that the null is incorrect, in other words, I agree or support the null when that is incorrect. So when there really is a difference in the two schools, but I think there isn't, then perhaps I don't do any interventions at a school that needs it more. You could justify either one as which one would be worse. Either one could take funds away from one school and give it to the other, or not take away funds and keep funds away from a school that needs it. Either way, the harming or potential harm to the students could be justified as a problem with that error. In our case, we concluded that we would need to fail to reject the null, so the type of error we could have made would have been a type 2. Okay, we're going to skip this one for now. Actually, I'll just introduce it, but skip the state plan do conclude steps here. You have two different people, or two different groups that were given potentially helpful drug to reduce cholesterol levels. So about half the participants got the drug, half took the placebo. Now, over the course of the next 5 years, so this was a pretty long-range study, the proportion of them that had heart attacks was monitored. So did it produce significant results? Did the gemcitabine actually help reduce the rate of heart attack? So I just wanted to introduce this one as showing you what the calculator would look like. So the two proportion z-test, we have to put in the number and the sample size of each group. So there were 2,051 men in the first group. 56 of them had heart attacks in that 5-year study. 2,030 were in the placebo group. 84 of them had studied. Once again, just like in 9.2, X has to be a whole number. So if it had been given to us a little differently, if it had said 5% of the group had heart attacks, we need to figure out what 5% of the 2,051 is, just as an example. Put that in as X as a whole number, not a decimal. So I would need to round if it was given to me as a decimal value. And then don't forget to put in your alternative. So if we are hoping that the cholesterol drug reduces heart attacks, then P1 would be less than P2 as the alternative. Hit calculate. There's your Z score or your Z test statistic that you need to write down. Your P value, so 0.0067 or 0.068 if you want to round it out, round it up because of the 5. Then the P hats and the P hat without the subscript, there's your PC. So this is could be used as a shortcut to get your PC if you're using your calculator to check your work, but you want to still show the formula to ensure yourself of partial credit if something has gone wrong. So there's your P1, P2, and PC down at the bottom. But really the only things that are required from this calculator printout is your Z test statistic and your P value that you would make your conclusion with. In class, we next looked at whether there was any difference between two states in a similar region of the U.S. In terms of their cancer rates. So pause for a minute, take a look at the questions that are available on OneNote. For instance, look at Maine and New Hampshire. Do they have similar proportions of cancer cases or different? Okay. That brings us to the end of 10.1. Next class, we will talk about the 10.2, the 2 sample T, and that will be the last new section in this unit. So please let me know if you have any questions.